Welcome to my channel. If you're new here, welcome, and make sure to hit that like and subscribe button for more fun physics content. Also, make sure you leave a comment down below if you have any ideas for any cool experiments we could do in the future. So today we're going to be taking a look at circuits and how the conservation of charge and the conservation of energy play a role in these circuits. So let's get started. I wanted to start by giving you guys a little background on some of the overarching physics concepts we'll be looking at today. The first is the conservation of charge associated with the node rule. The node rule explains that the current going into an element of a circuit will be exactly the same as the current coming out of that element of the circuit. Similarly, the conservation of energy via the loop rule says that the potential difference across one iteration of a circuit is going to be zero. We'll be using these concepts today as we look at a couple of circuits. The first circuit we will look at is a simple circuit including two 1.5 volt batteries, two ammeters, which measure current, and two resistors of 147 ohms. My first task was to estimate the current that will register in each ammeter. Because of the node rule, we know that charge should be conserved throughout the circuit, and thus each ammeter should have the exact same measurement. Using the equation potential difference equals resistance times current, I can take the potential difference, which is 3 volts from the batteries, and the resistance, 147 ohms. When I checked the math with my circuit online, you can see here that the ammeters read the same as my calculation. I was curious as to what would happen if I rotated one of my ammeters 180 degrees. After rotating them, I found that the ammeter still measured the exact same current as it did previously. Next, I replaced one of the ammeters with a voltmeter, which measures potential difference. When I do this, the remaining ammeter measures 0 amps and the voltmeter measures 3 volts. This is because the voltmeter is said to have an infinite resistance and thus does not complete the circuit. The potential difference it's measuring in this case is the potential difference of the batteries, as if the rest of the circuit didn't exist. I completed the circuit with a wire, returning the current to 0.0204 amps, and moved the voltmeter around each individual part of the circuit to examine the voltage. I compiled a spreadsheet of each element and the potential difference across that element. Notice that the sum of the potential differences of the resistors is equal to the potential difference of both batteries. This corroborates the loop rule because the potential difference gained by the batteries is canceled out by the loss of potential difference in the resistors, making the charge over the loop zero. This furthermore can be modeled by looking at the potential difference from one point on the circuit to each element in the system. I moved around one of the leads to each element before taking that data and plotting it on a graph. The electric field is the negative gradient of the slope, so you can see the specific spots where the electric field changed most rapidly and how the potential difference started and ended at zero. Using this information, you can calculate that the resistance of the wires and ammeters are 0, and the resistance of resistor 1 and 2 are 47 and 100 ohms respectively. An interesting thing to think about is the fact that when you're moving the voltmeter around the circuit, it changes the circuit, and yet the current flowing through the circuit does not change. This again comes back to the voltmeter seeming to have an infinite resistance. The same cannot be said though if you were to put one of the ammeters in parallel with a resistor. In this case, the current increases to 0.06 because the added ammeter has given some of the charge a place to flow that doesn't include the 100 ohm resistor. Next, I decided to take a look into capacitors. I created a circuit using a 9 volt battery, a 0.2 farad capacitor, and a 10 ohm light bulb. When you first connect the circuit, the light bulb flashes, then slowly dissipates. If you then connect the capacitor directly to the light bulb, the same process occurs again. When the whole circuit was connected, the capacitor was charging, causing the current to flow and stay in the capacitor. When the capacitor was directly attached to the light bulb, that stored energy dissipated through the light bulb. To model this relationship, I measured the potential difference across a capacitor with regards to time. Notice that as I track the potential difference, it increases in a rational curve that begins to even out around 9 volts. When you linearize the graph, you can find the RC value, which is the slope of the data, to be about 6 seconds. So that's all I have for y'all today. Tune in next time for more fun physics videos.